and the next 2 weeks, we are going to cover hazardous and solid waste management. So today we are going to cover hazardous waste management, and then if there is any spillover, then it will go to next week, and then we will start solid waste management. Okay. You can all hear me, right? Do I need to speak louder or anything?
No, ma'am, you're audible.
Yeah. Okay, so like I said, we are going to start with hazardous waste management, and that, along with solid waste management, is what we're going to cover in today's class and in the next two classes. So before we start, I'm going to ask you if you know what is solid waste. And there is an issue over here which I should highlight, and that is that even though hazardous waste can be in all three phases, meaning it can be gaseous, it can be liquid, it can be solid. We often put it along with solid waste for one simple reason, that when you have containerized hazardous materials, they are also considered hazardous waste. And whether it's because, for example, let's say you have a petroleum product, whether you have a paint can, whether you have pesticides, they're all in containers. So they still become part of solid waste. So it's because of the nature of the fact that when it is waste material, it is containerized, and therefore the container itself is considered, the entire thing is considered solid waste. Okay, so I've had people ask me questions, why is it in solid waste? Hazardous waste can be other than solid waste. The reason is because of the containerization of the waste. I will show you examples of spills and accidental spills, and also that is not solid waste, that is hazardous waste material, but not solid waste. So there are examples of that kind of waste material as well. So it's not a hard and fast definition, but I, for some reason, have, for this reason of containerization, I've included it in solid waste. But yes, you can have hazardous materials that are not in solid form. Now, I'll make that modification. So we have solid waste, and you can see 5 categories over here. You have municipal solid waste, agricultural waste, ash from thermal power plants, and industrial and mining waste. These are the 5 major categories of solid waste. And the way to define solid waste is that any material that is no longer of use to the person who is using it, the primary user, or even subsequent users, when it is thrown away and there is no usefulness attached to it, it's considered waste. And like I said, even gaseous and liquid materials that are in containers are called solid waste. So let's take a look at some of these examples that I've noted over here. Yeah, so let me go back to that. Let's start with, what should I start with? Let's start with agricultural waste. Agricultural waste is the biggest waste in our country. We are predominantly an agricultural economy, even though it's been reducing we've gone from about 80% at the time of independence to now about 50 to 60% of the GDP is from agriculture, but it's still our dominant activity. Okay. And when you look at agricultural waste in India is about 35% of the total solid waste. And if you compare with a developed country like the US, they have about 20% of their total waste is agricultural waste. Then we come to another huge category, and that is coal combustion residue. Coal combustion residue is nothing but a technical name for ash coming from thermal power plants. So when we use coal, you know that your thermal power plants, more than 50% of our electricity generation is based on coal powered thermal power plants. Okay, so this is ash. There are two types of ash. There's bottom ash and fly ash. The two together are called coal combustion residue. So this is about 25% of the total. And you can see it's a huge chunk. And I think for the US, the data has been clubbed over here. So they have included thermal power plant waste in their industrial and mining waste because that's the biggest chunk. That's about 60, more than 60%. Okay, so it's not that it doesn't exist. It just means that it has been clubbed in a different category. What is important from our point of view, and in the next class, we're going to focus on municipal solid waste. So that is for the next two classes. And you can see we have a huge amount. 11% of our total solid waste of is from the municipal solid waste. Now, municipal solid waste is basically coming from the cities, from urban centers. We're not looking at the rural areas where you have residential waste as well as agricultural waste. So we're not going for that. Municipal solid waste means waste that is generated in urban areas. Then we come to hazardous waste. And you can see that a developed country like the US has a huge amount of hazardous waste as a fraction of the total waste compared to a lesser developed country like India, which has a very small fraction of the total in the form of hazardous waste. Now, one reason is because we are not as industrialized as the other developed countries. That is one reason. The second reason is that we are not really focusing on hazardous waste in terms of quantification and so on. I think there may be issues of quantification. So that may be the reason why it's such a small chunk of the entire waste. So I think I've covered most of it. Let me say something about industrial and mining waste as well. So you can see, because again, for reasons of lack of industrialization in comparison to the developed countries, so our industrial waste is slightly less than 30%, and you can compare it with a country like the US, which has more than 60% industrial and mining waste. So I think they have clubbed together industrial, mining, and thermal power plant waste. So all of that comes because their electricity usage is much greater and the number of thermal power plants is greater. Everything is much higher. So that's probably one of the reasons. Okay. And we will be focusing in this class on hazardous waste, and I will come to all the definitions that are mentioned here. I'll come to that in the next few slides. Before we go too far, why should we worry about solid waste management? So like I said, I've taken a particular perspective, which again, there are some contradictions here, so we'll have to deal with that. But I've taken, the focus has been on solid waste management. And in our country, we are particularly most of us have been looking at open dumping. I think if you look around your city, you'll find some dumps where both residential waste and perhaps even waste from industrial, small and medium industries, if they are operating in your area, you can probably see dumps. I can tell you that 20 to 30 years ago, these were a common sight. And thankfully, the number of dumps that you can see around you has definitely reduced, but they have not disappeared. They're still there. So what is the problem? What are the hazards associated with open dumping of solid waste? Whether it's of a hazardous nature or whether it's municipal solid waste, either way, it's bad for the environment. And the question is, what are the hazards of open dumping? So if you dump any material in the open, whether it's hazardous or non-hazardous, when the material is released into the air, it's going to be scattered by wind. There will be some amount of degradation, which will lead to the generation of what we call volatile organic compounds, and these will volatilize. So anytime you pass by a waste dump and it is stinking, that's because of volatilization of certain compounds, volatilization of gases. All that will lead to air pollution. So that is the first one. The second one is the potential for explosions due to methane buildup. Most of you must have noticed, especially those who are from Kolkata, it's so obvious. When you come from the airport and head towards the south, I think, yeah. So you can see these huge landfills. You know, they're not proper landfills. They're just open dumps of municipal solid waste, and you can see a lot of smoke coming out of them. So that smoke is because of fires within the dump. So people put anything and everything in the dump, and that material catches fire. Whether the fire is caused intentionally or unintentionally, that is a lot of air pollution, and the fires are self-sustaining because of the methane that builds up within these landfills. And the methane builds up because of the degradation of organic matter. So biodegradation of the organic matter leads to the buildup of methane, and methane is a very flammable gas. So whether it's whether the fires are lit intentionally or unintentionally, it doesn't matter. The potential for explosion is there, and the slow burning fires, which you see in India all the time, that is also another major problem in terms of air pollution. So that's one big one. Then we come to water pollution. When you look at water bodies anywhere around you, you have surface water bodies, you have groundwater bodies, and in both cases, there is a huge potential for um, contamination of open water bodies, these surface water bodies, as well as the subsurface water bodies. And one of the things that has become a real problem in the last few decades is clogging of what I would call natural drainage systems. You can see, especially in the monsoon, when and why does water logging happen? You look at the urban centers, you find that there is water logging during the monsoon in almost every town and city in this country. We know that when it rains, it literally pours, right? So there's a huge amount of rainfall that happens in a short period of time. Now, nature has created drainage channels. It's a natural process. Nature creates drainage channels which allows all this rainwater to go to any open surface water body, right? If you construct roads and buildings across these channels, across these natural drainage systems, what will happen? You're preventing the natural flow of water into these open water bodies. That's a huge problem because most people who are doing this kind of construction are not aware of these things. And even when you have engineered drainage systems, if they are filled with waste, and that happens anywhere, you can go around any town or city, um, you will find that the nalas, the constructed nalas as well as the natural nalas, all of them are often clogged by waste, and that waste can be from natural waste. It may be trees and leaves and twigs and branches and all those kinds of materials, or it may be municipal solid waste. It can be anything. So when you have clogging of natural and engineered drainage systems, not only are you causing water pollution, but that is also one of the biggest reasons for water logging in urban areas. Then we come to short-term and long-term contamination of non-renewable resources. I already mentioned in the topic on water pollution, I said that groundwater pollution is very, very difficult to remediate. What in surface water, you have a self-purification capacity of a stream. But in groundwater, you don't have that. There's no self-purification capacity. So once the groundwater is contaminated, there's very little you can do with it unless you're willing to treat it at great expense. So it's a huge effort in those cases. And this will result in short-term as well as long-term contamination of what are practically, this groundwater is practically a non-renewable resource, okay? It takes tens to hundreds of years to renew itself. So from a practical standpoint, we consider it many times to be a non-renewable resource. Surface water, on the other hand, has a self-purification capacity, which allows it to be, uh, if you prevent the pollution source from discharging, then obviously it stops. Then we come to soil pollution. Now, if you have a lot of waste dumped on open soil, There are contaminants in the soil which will attach themselves to the soil matrix. So this is called sequestering of contaminants that leads to soil toxicity, and eventually it will reduce the productivity of the soil. And productivity means in terms of agricultural productivity. That's what we are interested in. Then we come to health hazards, not less important, but it's also one of the most important reasons. What is one of the biggest problems with these open waste dumps? One of the things is that these dumps become a sort of focal point for the growth of pathogens as well as what we call vectors. So you have flies, you have rodents, you have mosquitoes, all these kinds of rodents, meaning rats and mice, and these kinds of pestilent species that are going to be attracted to the waste, and they will cause the release of pathogens. And there can be several, and in fact there was an epidemic in 1994 in Surat. There were a very few number of towns that were affected. The biggest one was Surat, and it was because of it was a sort of combination of bubonic and pneumonic plague, and the vector in a plague is basically fleas and rats. So you have a bacteria, Yersinia pestis, that's picked up by the fleas. The fleas transmit it to the rodents, and these rodents, if they come in contact with human beings, they will transmit this particular bacteria to human beings, and it can be fatal. So this was, in fact, what happened in 1994. So there is a huge potential for diseases because of these open dumps. Then we come to stray animals. And this is something, the last point is something that you have probably all observed. It's a common sight even in our campus. Even within the building, this happens all the time. You have cats and dogs that come into the buildings, they topple over the trash cans, and they scatter the waste. Now, if this happens on main stretches where you have heavy traffic, this will contribute to bad traffic conditions, and to a certain extent, it can have an accident potential. Okay, so I often find it when I'm driving that I find cats and dogs and other animals, they stray across the road because they are attracted to this waste material for as food, and that contributes to all kinds of traffic problems. And then the last ones are related. I think in my introductory lecture, I said a lot about aesthetics, civic health and pride, and property values. So this is again another very good example of how these three fundamental principles come together, because you have to realize that anytime the aesthetics of a particular neighborhood go down, there is loss of civic health and pride. Your public health goes down, automatically public and civic pride, etc., goes down, which leads to lower property values. And these lower property values make the whole point of managing waste becomes difficult. Remember that the municipalities are living off the revenue from property taxes. So one of the major sources of funds for managing any municipal area is property taxes. And when the property value goes down, automatically property taxes that are collected will also go down, and it's like a vicious circle. So unless things get better, nothing gets better. So it's a very difficult situation for most Indian urban towns and cities. Then let's go through a little bit about environmental regulations before we come to the details about hazardous waste management. I think again I mentioned something about regulations perhaps in previous topics, maybe not. Let me see. So regulations in India that are related to the environment started as far back as 1974. That was the first one. It was the Water Prevention and Control of Pollution Act. It's been, all of them have been amended more than once. And the Water Act was followed by the Air Prevention and Control of Pollution Act in 1981. There was realization that to have specific rules and regulations governing pollution of two major parts of the environment was not enough, because that did not take care of ecosystems, that did not take care of watersheds, that did not take care of the environmental impacts that were broad-reaching impacts, very far-reaching impacts that were beyond air and water. You can have soil problems, you can have noise issues. There are so many issues that you can have, and those were not being covered by the first two acts. So then came the Environment Protection Act. This Environment Protection Act basically gave the government far-reaching rights to monitor all kinds of pollution in any part of the environment, and it made environmental impact assessment became mandatory for large projects. So anyone wanting to do a large project had to do an environmental impact assessment, and that had to be basically put in the public domain, and all these kinds of discussions that we see in the media all the time, that is all part of the Environment Protection Act. And what we're going to look at in a little bit is the hazardous waste management and handling rules. So after having taken care of a sort of holistic part of the taking a holistic view of the entire environment, then there was realization that specific types of waste need to be handled in a specific way. So the most important one was hazardous waste, and this was rules were put into place in 1989. Then came biomedical waste. Now, biomedical waste is also, from a technical standpoint, it's a hazardous material. However, it was being ignored under hazardous waste management and handling rules. So in 1998, there was a special set of rules made just for handling biomedical waste. And you can understand, especially under this set of conditions, under the COVID-19 pandemic, you know that there's a lot of talk about biomedical waste and how is it being handled. So there are specific instructions how to handle biomedical waste, whether, like I said, it is from a technical standpoint, it is also hazardous waste, but it is of a different nature. So we're not going to go into any details for the simple reason that we don't have enough time, but it's a very important regulation. Then we come to fly ash. I already mentioned where fly ash is coming from. Okay, so I already mentioned to you that when you burn coal in thermal power plants, there are two types of ash that are generated. One is the ash that falls within the furnace, it falls to the bottom, and that is literally called bottom ash. And when the flue gases, when hot gases are released in the burning of coal, these gases go through the smokestack. When these gases are rising, very, very fine particulate matter also goes into the atmosphere along with that, with those flue gases. They are called flue gases, FLUE. So these flue gases contain particulate matter, and this particulate matter is respirable particulate matter. So it's so fine that it can enter the lungs. And people who live in highly polluted cities like Delhi and Kolkata, which are considered one of the most, these are the most polluted cities in the world. They are, I think, in the top 10 list. So in these cities, the respirable particulate matter is extremely high, and it is a serious health hazard. And I remember the days when you can drive by any of the roads around the thermal power plants, and you will find these huge piles of what looks like cement, but it's not cement, it's fly ash. Okay, it looks just like cement. It's that fine, and like I said, it's a huge hazard. So a separate set of rules were put into place just for handling fly ash. And today, according to the rules, all of the fly ash has to be utilized in creating bricks. So all the brick kilns in a particular, I think the radius is 50 to 100 kilometers radius around the thermal power plant. All of the fly ash has to be used in the generation of bricks so that it gets completely reused. The next one has, I think, become obsolete because it has been this particular set of rules has been replaced by the Plastic Waste Management and Handling Rules of 2009. So I won't say anything about it. Then comes another major turning point. Another major turning point is Municipal Solid Waste Management and Handling Rules. These came into effect in 2000 and they've been amended, and now they are simply called Solid Waste Management Rules. Municipal solid waste rules. Yeah. So this, like I said, is a major turning point because it puts the onus of responsibility for managing solid waste on the urban authority. So whether it's a municipality, whether it's a municipal corporation, in small towns or villages where it's the district magistrate, whoever is the administrative authority of a particular location, that administrative authority is fully legally responsible for providing proper management of the waste. So by putting so much responsibility, there was no rule to this effect. Okay, so having a rule to this effect means that the urban local body, whatever it was, has now got the responsibility of providing collection, treatment, and disposal of solid waste in a proper manner. Then we come to batteries management and handling rules, and that is in 2001. These batteries are not your regular batteries. These are the batteries that we use in vehicles, in converters or inverters, whatever you want to call them. These are lead acid batteries. So lead acid, as you can understand from the very name, lead is a toxic heavy metal, and these lead acid batteries have a high acid content as well as a high lead content, and they cannot be handled by the common man. So the major point about the batteries management and handling rules is that anyone using a lead acid battery has to return the battery at the end of its life to a registered dealer, recycler, an authorized person basically, and you cannot just dismantle it on your own, and you cannot do whatever you want with it. So you have to buy it from an authorized person and you have to return it to an authorized person. So that is the main point over here. And these batteries have to be recycled in a proper manner. As I said, plastic waste has been, there have been several rules and regulations about plastic waste management, and the most recent one is in 2009. This has to do with reducing the use of single-use plastic. It's got to do with collection and reuse as well as recycling of plastic. So it's got a lot to do with that. Then we come to e-waste management. So most of you have probably realized that the amount of e-waste in our homes and offices, schools and colleges, everywhere, it's just rising for obvious reasons. Most of us are stockpiling e-waste. So everyone realizes it, including the government, that something needs to be done. So starting in 2011, there are authorized recyclers. There are centers that have been created for formal recycling. So you have dismantling of the e-waste, you have recycling of the e-waste, all these things. And e-waste there are several major points in e-waste management, but I'll just say a couple of things over here. In e-waste, One thing is extended producer responsibility. So, unlike municipal solid waste, where I am the generator of the waste but I'm not held responsible, in e waste it's the other way around. Whoever manufactures an electrical or electronic product is going to be held responsible for that product until the end of its life. Okay, so that is called extended producer responsibility. Now, this extended producer responsibility is one part of it. The second part of it is registration of authorized dismantlers and recyclers. These people have to show to the government that they have appropriate safety measures for protecting the health of the workers. They have adequate protection from and prevention of pollution of the environment. So everything is done in such a way that the health of the workers as well as the um, pollution of the environment is not compromised. And that is unfortunately not the case with the informal sector. So if you go to certain areas, there are certain particular locations in this country, um, perhaps in many states. Delhi has one, Kolkata has one, West Bengal has a place called Sangrampur. In UP, there is a city called Moradabad. Um, Delhi, like I said, has a particular location. I've forgotten the name of this location, but they're all becoming world famous for recycling of e-waste, and it's all done in a very shoddy manner. So it's not only illegal, but it also jeopardizes the health and the environment. So these are major rules that have been put into place to prevent this kind of thing from happening. And it's still happening, but those are difficult stories. So anyway, then we come to the last one, which is construction and demolition waste management rules. That's the most recent one in 2016, and that is for taking care of the waste that is generated in both construction as well as demolition projects. Even in campus, you can see many of the old buildings are being brought down, and there is a huge amount of waste of all kinds. So you have cement, you have concrete, you have aggregate, sand, metal, wood, all kinds of materials are uh, bro- brought into the waste stream. And even in new construction, you will find that all kinds of materials are part of the waste stream. So this kind of waste has to be given special attention. Okay, that's all about the general overview about waste. And I always make another point here. And one of the major things that I want you to notice is that after the Environment Protection Act, you look at all the other rules, they're all related to solid waste streams, most of it. So, has waste and biomedical, you might say, has a liquid stream attached to it, but the rest of them all have solid. They're basically solid waste. Let's take a look at why we need to go through hazardous waste management. What are the problems associated, particularly with hazardous waste? So the first thing is the law. Um, I don't know how much you notice or how much you have an opportunity to even see this, but in general, hazardous waste management is driven by regulations. For mainly one reason. All industries that are generating hazardous waste will not do anything about it unless there is the law behind it. Okay, so I cannot walk into any industrial premise and say that you are doing something bad for the environment. There has to be a legal framework within which somebody can point out that yes, this particular activity or this particular factory or industry is causing harm to the environment or to the health of people around them. So the first thing is that yes, it's a public health concern, and in general, it's driven by the law. And what are the concerns underlying the law? They are of they're twofold as usual. Almost everything that we do related to the environment has two major concerns: public health concerns and environmental concerns. So there are several examples of toxicity due to hazardous materials and the diseases associated with exposure to those hazardous materials. And there are any number of examples. I've just written 2 or 3 of them. So Hiroshima and Nagasaki are famous. You're all aware of that radioactivity is a major source of health hazard. So Hiroshima and Nagasaki are both of them examples of that. That's the beginning, really, when people started realizing that there are certain materials that can cause enormous damage to public health. And then there is a very celebrated example called Minamata disease. Now, Minamata disease, which I will perhaps come to later, let me see. So Minamata disease is related to another very interesting incident. I don't want to call it an incident. It was over a period of more than 10 years. So from the early 50s, so like let's say 1950 onwards, there was a fertilizer manufacturing company. Minamata is a town on the coast of Japan. There was a fertilizer manufacturing company called Chiso, and they, in the process of manufacturing fertilizer, they were using a particular catalyst, and that catalyst was containing, it had a mercury amalgam in it. Now, when the wastewater from this fertilizer manufacturing plant was being discharged, I think it was being discharged without any treatment, it was going directly into Minamata Bay. Now, this material was contaminating the Bay Area, and the people in this particular town were utilizing fish and other food materials from the same area. Over a period of time, maybe in 1958, I think, in 1958, in 1958, it became apparent to people, not just in the local population, but even to outsiders, that something was very seriously wrong with this particular town, because the residents as well as the animals in this particular town were behaving in a very strange manner. So the human beings, cats, birds, and several other types of animals were all affected by strange behavior, and the strange behavior is indicative of neurological problems. Okay, and eventually it took them a fair amount of time for them to figure out that the levels of mercury in all of these organisms, let's call them, including human beings, were very high in comparison to other towns. So that's why it's called the Minamata disease, because the mercury in the wastewater had become methylated. So it was methyl mercury, and methylated mercury has a tendency to accumulate in the tissue of all organisms, whether it's human beings, whether it's fish, cat, dog, whatever it is. Okay, so because the people were feeding on the fish, which was heavily contaminated with methyl mercury, so it was accumulating in the body of all the organisms that were exposed. So this is, like I said, one of the biggest examples of a hazardous material being being discharged into the environment, and because of that there are severe problems down the line. So it took them more than 10 years to figure out all these things. And then what happened in Bhopal in 1984 is another very dramatic example, but that is not a that was something that happened over a very short period of time. So that was a literal accident when phosgene gas was released. There is a huge difference between the two. Minamata was intentional release. It was not accidental. Bhopal and Valdez and all these others are accidental releases. So there are two types of spills or releases of hazardous materials. It can be accidental or it can be intentional. So either way, they can cause a lot of damage. And in Bhopal, what happened was phosgene gas, which is extremely toxic. It's also called methyl isocyanate. And this was released, and thousands of people were affected because it was released into the atmosphere in the middle of the night. So most people were caught unawares, and it became a huge problem. Then we come to environmental concerns. So the first thing, like I said, is always public health concerns. And then the second thing is, are other species besides human beings being, are they affected? And for those of you who remember, the Exxon Valdez oil spill occurred in 1989 when crude oil from a particular tanker, it was a huge tanker, that was spilled into Prince William Sound in Alaska. So um, hundreds to thousands of kilometers of beach was destroyed. Aquatic ecosystems were completely destroyed. The birds, all these other organisms. There's a lot of media attention and all of that. So we'll go through some of these things, and there are some other examples over here. I've covered most of them. Then there is radioactivity release in 1986 from a nuclear Chernobyl nuclear power plant disaster was another big one. And the last one, which I will cover again in some detail, is 1992. This is related to a big extent to e-waste, even though it's not just about e-waste, it's got a lot to do with e-waste. And that is called the Basel Convention on the Control of Transboundary Movement of Hazardous Waste. Now, e-waste is one of the major waste categories that has been part of the illegal import-export of waste materials from developed countries to developing countries because of the expense of waste treatment. So this convention came up with a, an agreement, a global agreement that most countries have signed to prevent this transboundary movement. However, there are major issues. The illegal trade continues even to this day. Okay, so there's nothing you can do because between countries it's all by agreement. There is no legal recourse in that sense. Okay, we'll come to some other issues. Publication of Silent Spring. That was another milestone in the environmental movement. So in 1962, Rachel Carson published The Silent Spring, which was about the impact of pesticides mainly. So people had begun to notice in the 50s and 60s that pesticides were being used and abused rampantly. People were spraying it all over themselves and over their fields and gardens and all. It's unbelievable. When you read her book, you might be able to understand that. So it became more and more obvious that there was excessive use of pesticides and it was causing very serious public health problems at the individual level. So individuals were being affected and so was the ecosystem in many areas. So all these kinds of things became obvious, and Rachel Carson put together a lot of stories from the media as well as from her research and so on. And that was a major milestone, like I said, in the environmental movement, because people began to realize the harmful effects of these kinds of chemicals. So we are going to look at hazardous waste management and look at some of the short-term and long-term health problems associated with exposure to hazardous material. We know that there can be long-term damage to the environment and to the air, water, soil, all of this. And the biggest issue that is associated with hazardous or toxic compounds is bioconcentration. So there are three terms that we use: bioconcentration, biomagnification, and bioaccumulation. And I think you have already done some work in that area. Yeah, I talked about this when I was talking in the introductory lecture. So this is one issue that is of primary importance when we think about hazardous materials. Now, where is management required? There are two major categories of situations that I've put in here. There may be others. One is, like I already said, accidental or intentional releases of hazardous materials that we have already seen. The next one is industrial sites. You don't see it so much in India, at least I haven't seen too much of it. But in developed countries, this is a huge problem because their industrial history is close to 150 years old, and for us it's not more than 70 to 80 years old. So because of that difference, you see a lot of old and defunct industrial sites in developed countries, and nobody wants to buy property next to these industrial sites. So this is good property that is lying waste, or because it's a potential environmental problem. For many reasons, these old and defunct industrial estates or sites are a huge problem. So people want it to be closed. They want these sites to be closed or reclaimed. And that's a huge area of work in developed countries in the last few decades. In fact, I've actually seen the transformation of many urban cities. So Singapore is one example, Baltimore is a second example, where these were industrial cities. These you can literally go to these cities and you will see how dramatic the transformation is. These were old industrial cities that were heavily polluted, heavily contaminated, and then over a short period of time, the municipalities decided to do a complete makeover, and you can see the results for yourself if you ever get a chance to go there. To some extent, Ahmedabad too, but not so dramatic. Yes, there is some of that. Okay, like I said, we need to focus on the Basel Convention. It's one of the most important international treaties. And it's basically the objective is to ensure that developed countries do not export their hazardous materials to developing countries. You can understand the economics of the process is highly attractive because developed countries find it very expensive to treat hazardous material, and developing countries are always hungry for money from the developed countries. So this, on an economic basis, is what encourages the illegal trade, the import and export of hazardous materials from developed to developing countries. So this international treaty, which has more than 182 countries that are already signatories to it, this was signed because philosophically and in principle, everyone agrees it should not happen. But like I said, the most unfortunate part of it is that the economics of the process is the driving force. And the cost of treating hazardous waste is very high, and developed countries find it easy to export. And there's, like I said, there's no global policeman, so that doesn't work. Yeah. Um, but there are subsequent there are some other things that have happened after that. So there is the Basel Convention, there is BAN, that's the Basel Action Network that has been created to ensure that the Basel Convention is implemented by these countries. But again, like I said, it doesn't have teeth. And the UN has another body that is responsible for doing that. But we all know how that works. Okay, let's stick to our home regulation. So here we have hazardous waste, and the hazardous waste management handling rules have been modified now to say hazardous waste management handling and transboundary movement rules. And that is to ensure that there is no illegal import of hazardous waste, including e-waste. Um, there is a lot of that. So shipping waste, e-waste, these are some of the things that have been imported illegally into our country, and that is really not allowed by these rules. Okay. So how do we define hazardous waste? The first thing is any waste which, because of its physical, chemical, reactive, toxic, flammable, explosive, or corrosive nature, is a danger to can cause danger to either the health or the environment. And this is considered hazardous whether it's by itself or in contact with other materials. Now, I'm not going to go into any of the details. The rules have specific schedules, and the waste from the industrial processes are listed in Schedule 1 or Schedule 1, and those having constituents with based on concentration are listed in Schedule 2, and there are certain lists of A and B in Schedule 3. So in fact, I will upload, what I'll do is I'll upload the latest version of these rules, and that way you can at least go through them. Now, within the rules, there are certain exceptions. So the first exception is wastewater and exhaust gases. It's not, these 6 exceptions are not exceptions because they are non-hazardous. They are exceptions because they are so specific in their nature that they deserve separate rules for themselves. So wastewater from, let's say, industries comes under the Water Prevention and Control of Pollution Act, and exhaust gases again from industries is again driven by the other act, the Air Prevention and Control of Pollution Act. If there is waste coming from ships that are beyond 5 kilometers from the coastline, they are governed already by the Merchant Shipping Act. So you can see that the Merchant Shipping Act is very old in comparison to the hazardous waste rules, which are 1989. So since they were already governed, so they become an exception. And I've also mentioned the regulatory body. Now, for all of you, it's very important to remember, for all the other rules, what is the regulatory body? The regulatory body in India is Central Pollution Control Board, CPCB. CPCB is the monitoring authority. They are the administrative authority, and every state in the country has a state pollution control board. So West Bengal has its own pollution control board. Gujarat, Maharashtra, Rajasthan, every state has its own. They are required to have their own state pollution control boards, and these state pollution control boards are answerable to the central pollution control board. So annual reports have to be submitted with all the required information and so on. Okay, so wherever the regulatory body is not mentioned, assume that it is either the State Pollution Control Board and or the CPCB. So if I say State Pollution Control Board, it's automatically CPCB because the SPCB is answerable to CPCB. So then we come to the shipping waste, where the regulatory body is not CPCB, it is the Director General of Shipping. Then the third category is radioactive waste, which is already covered in a very old law, and that is the Atomic Energy Act, which is 1962. The regulatory body is the Department of Atomic Energy. Then we come to biomedical waste under the Biomedical Waste Management and Handling Rules. That's a separate act, again under CPCB. Then we have municipal solid waste, which is again governed by CPCB. And then finally, the lead acid batteries, which are again governed by the Batteries Management and Handling Rules under this act, but under this particular act. And that's again under CPCB. Now, that's all about the law. Is the law and science always the same? Not always. So here we have some technical categories. Now, different books might have different categories, but this is one set of categories. And you can see hazardous waste can be chemical, industrial, or household hazardous waste. Now, household hazardous waste includes your dry cells, your disposable batteries, tube lights, thermometers, all paint cans, pesticide cans. These are the things that we use on a daily basis, and then we know that they're all hazardous in nature. So all the other categories we know are hazardous, but Here are more examples of those kinds of waste. Nuclear waste, everyone knows, has radioactive characteristics and therefore it's hazardous. Biochemical waste is hazardous because of the infection potential associated with the biomedical or biochemical waste. Now, biomedical and biochemical are slightly different. Biomedical comes from hospitals, pathology labs, nursing homes, clinics, and so on. Biochemical waste includes all of that and perhaps pharmaceutical companies and so on. So that is biochemical waste. E-waste comes from electrical and electronic appliances. So all electrical and electronic appliances after their useful end of life are considered e-waste or electronic waste for short. And then we come to sludge. Sludge from municipal wastewater or water treatment plants, all of that is also considered hazardous waste. The next thing is, how do we identify a material as hazardous waste? Before I come to the definitions, let's look at the nature of the waste. There are three types of waste streams. You can have undefined mixtures, you can have specific substances, and you can have specific waste streams with known compositions. So try to imagine an industrial facility and think about the wastewater coming out of these facilities. It may be pharmaceutical companies, it may be paint industry, it may be electrical or electronic goods manufacturing industry, it may be anything that you might think of as creating hazardous materials. Okay, now if that waste stream is of unknown composition, I don't know what is in the wastewater, that is an undefined mixture. The wastewater is automatically an undefined mixture. If there are containers of waste, for example, the UCIL plant, after the Bhopal gas tragedy happened, the plant was shut down, nothing else was there. But what was found on the site was barrels and barrels of chemicals. No one knew what there was. It was waste chemicals, but no one knew what it was. So that's another example of undefined mixtures of hazardous waste. In many industries, you'll find that waste materials are known. You ask the officials of that company what is in this container, they will be able to tell you that this is a specific chemical. So those are specific substances. Similarly, with defined waste streams. So in many cases, the company officials or the industry officials will be able to tell you that this particular waste contains A, B, and C chemicals. So that is the third one. So these are the three possibilities that exist when you're dealing with hazardous waste, especially from industrial sites. Then we come to waste that is identified as hazardous. So what are the definitions? The first one is ignitability. Then we come to corrosivity, reactivity, toxicity, radioactivity. NERI has its own, those of you who don't know what NERI stands for, National Environmental Engineering Research Institute. That's within our country. And they have some other definitions they would, I think, like to include, and that is infectivity, phytotoxicity, and mutagenicity. Let's take a look at each one of these criteria that will be used to define any material as hazardous. So the first one is ignitability. Any waste that has a tendency to catch fire during the process of transport, storage, treatment, or disposal. So if you have oils, solvents, flammable gases like methane, flammable compressed gases, strong oxidizing agents, all these would qualify as hazardous waste because of the possible potential for catching fire. Any liquid with a flash point less than 60 degrees centigrade. You may have heard about what is often called spontaneous combustion. It's not really spontaneous. You need a spark, but some of them have a vapor pressure that is quite high. So let us say at 60 degrees centigrade, which happens very often in our environment, the amount of that particular chemical in the vapor phase is going to be fairly high. And if there is a spark in the environment, it can catch fire and lead to an explosion. So that is about liquids with flash points less than 60 degrees centigrade. If it's not a liquid but under standard temperature and pressure, if it can catch fire due to friction, friction creates sparks, and absorption of moisture under certain conditions can create fires, and spontaneous combustion or spontaneous chemical reaction can also lead to fires. Then we come to reactivity. Any waste that is highly reactive is considered unstable and therefore hazardous. So it can lead to fast reaction rates, and extremely fast reaction rates is what we call an explosion. So explosions are basically defined as extremely fast reaction rates. And these series of reactions, if they happen very fast with or without detonation, so with or without explosion or detonation, is considered highly reactive. There are certain chemicals that can react violently with water. You know that you take any simple strong acid, sulfuric acid, hydrochloric acid, any of them, if you add water to the acid, it will react violently and it will create an explosion, and it can be extremely dangerous. So that's a potentially dangerous mixture with water. So anything that is explosive, toxic, and if the fumes, the vapors or the fumes are also toxic, then they all qualify to be considered hazardous materials or waste. So cyanide and sulfide bearing waste that has a pH range of 2 to 12.5. Corrosivity is waste with very low pH or very high pH. So anything that is highly acidic or highly basic, that would be corrosive, and therefore it's hazardous material. Anything that is poisonous at any concentration is also considered hazardous. So if it is toxic, if it is poisonous to any organism at any concentration that you're likely to see in your environment, that will be hazardous. I've already mentioned infectivity. If the waste contains viable microorganisms or their toxins that are known to cause diseases in animals or humans, that would be considered infective waste and therefore hazardous. So that's why biomedical waste has its own set of rules. And then we have phytotoxicity. Any material that has a toxic effect on plants. Phyto means plants. So anything with a toxic effect on plants is considered phytotoxic and therefore hazardous. Let us take a look at some other words that we use to define hazardous. Now, like I said, we need to define a few things for understanding the next set of terms. So whenever we think about the health effect of any contaminant, we use certain terms. There are two categories over here. The first two categories are genotoxic and cytotoxic. Genotoxic, as the word implies, is something that damages the genetic structure of the organism, so the genome or the genes of the organism, and any damage to the genome is going to be called a mutation, and therefore it's mutagenic. Mutagenic means generating mutations, so that's mutagenic. Let me finish this, and then cytotoxic is easier. Cytotoxic, cyto stands for cell, and any damage to the cell is considered cytotoxic. And you've all experienced it at some point or the other when in the lab, you know that Anytime acid falls on your skin or you get a slight drop or something that gets into the eye, what happens? Your eye or skin may turn red. So those are examples of cell damage. So those are simple daily examples of cell damage because of the cytotoxic effects of that chemical. Let's come back to genotoxic. So genotoxic, if there is damage to the DNA, that will result in mutations, and the mutation that if that chemical is causing damage to the DNA, it's called mutagenic. Now, most mutations tend to die off. So let's say there are millions to billions of mutations happening on a daily basis. Most of them will die off because they are not able to survive. However, that rare mutation that does not die off naturally is going to result in a tumor. So that becomes tumorigenic. Now, this tumor can be of two types. It can be benign or it can be malignant. Malignant means it spreads to the tissues and organs throughout the body of the organism. And benign means it's not spreading, it is contained. And it's really runaway growth. The mutation will cause runaway growth of the cells, and as long as they are contained and creating a tumor which does not invade the other organs and tissues of the body, then it's benign, it's removable. But if it starts invading the other organs and tissues of the body, it becomes carcinogenic, so it becomes malignant. And then we have teratogenic effects and reproductive defects. Now, most of you have probably heard about, how reproduction works. So you have haploid cells in the form of sperm and ova, and if there is damage to these haploid cells of human beings, that will result in reproductive defects. So you can have infertility, miscarriages, and so many other kinds of problems. Teratogenic effects is the last category, and that is any compound that affects the embryo or the fetus while it's developing, leading to low birth weight, mental or physical defects in the child. That is all teratogenic effects. So that in a nutshell is all of it. That's a heavy dose, isn't it? Yeah. Let's take the next characteristic of hazardous waste. The next one is radioactivity, and I think you have studied radioactivity at some point, but let's revise it and make sure we are all on the same wavelength. So you know the atomic number is the number of protons, atomic mass is the sum of protons and neutrons. These are the symbols that we use. Z is the number of protons, A is the sum of protons and neutrons, number of neutrons is N. Isotopes are defined as elements with the same atomic number but different atomic mass, and the way we write it is A, Z, and E is the element. Now, what holds the nucleus of the atom together? There are two types of nuclear forces. One is attractive, the other is repulsive. The attractive forces are strong, intense forces. They are independent of charge. They are very short-range forces that hold the nucleus together. And the repulsive forces are the electrostatic forces between positively charged protons. Let's take a look at this graph. So here we have N versus Z. That. So Z is our number of protons and N is our neutrons. So here we have neutrons versus protons, and the line, the solid line, is the line of equality between N and Z. So where N and Z is equal is your straight line. That's an abstract idea. The dots represent individual elements. Each dot is an element in the periodic table. You can see the deviation. After N is greater than 20, you can see the entire curve is falling away from the line of equality or equivalence. Yes, it's called the line of equivalence. And reality, you can see, is deviating from this line of equivalence after n is equal to 20. So as long as the number of protons is low, n is not exactly equal to z. You can check the periodic table for yourself. I think for the even numbers, n is equal to z. For the odd numbers, it's n plus 1. Yeah, because that's what is going to keep the nucleus stable. So z by n less than 1 for n or z less than equal to 20. So that's fair enough, okay? So at n is equal less than equal to 20, all is well, the nucleus is stable. You go beyond that, the degree of stability starts dropping. And at n greater than 83, it becomes radioactive. It's no longer stable. So n greater than 83, bismuth it has only one stable isotope. Repulsive forces within the nucleus will start dominating, and the nucleus is considered to be unstable or naturally radioactive. You can make any element artificially radioactive by shooting a beam of neutrons at it. Any questions at this point? I'm just going on and on and on. Do you have any questions? Okay. Obviously, no one has any questions. You're probably not paying attention. So anyway, reactivity is, we have seen that reactivity, or we talk about chemical reactivity, that is the instability of an atom or molecule. Radioactivity refers to the instability of the nucleus. So when the nucleus of the atom is unstable, that will lead to spontaneous breakup of the nucleus and result in these three types of radiation: alpha radiation, beta and gamma radiation. Alpha radiation, you remember, is helium nuclei, 2 neutrons, 2 protons. Beta radiation is electrons from a radioactive nucleus, and gamma radiation is just plain electromagnetic radiation. There are no particles associated with it, and it travels at the speed of light. What is important from our point of view are the units that we use to measure radioactivity and how diverse they are. So this is a list of the units, and I'll show you the definitions in the next slide. So here we have the radiation units. You can measure radiation in many different ways, and it all depends on what you are trying to do. So you will find that in many and this is not just about radioactivity, but about many other parts of science and technology, where we use certain ways of measuring based on our practical objective. Okay, so here we have units for radiation emitted, radiation absorbed, and what is the effect of the radiation. So each of the units is applicable for a particular practical point of view, or in a practical endpoint. So if I want to know how radioactive is a particular element, then this is the first set of units. So radiation emitted by a particular element or a particular mass of mineral or whatever it is that we are looking at, there are 2 units, curies and becquerels. Curie is now obsolete, but it was equal to 3.7 times 10 to the power 10 disintegrations per second, and this is considered the decay rate of radium. What is used today is becquerels. That's the SI unit. The Systems International unit is becquerel. Short form is BQ, and that is 1 disintegration per second. Then we come to radiation absorbed. Radiation absorbed is Rontgens. Rontgens are the number of ionizations. Now, I think you may have realized by now that when radiation is incident on a material, it will cause ionization of that particular material. So number of ionizations produced in a given amount of air because of the impact of X-rays or gamma rays can be measured in terms of Rontgens. And then we have radiation absorbed dose. Radiation absorbed dose is how much energy is being absorbed by 1 gram of any substance. So here we are not interested in what is being emitted, we are interested in what is being absorbed. So for example, when I go for a dental filling or something and they take an X-ray, I want to know how much of this radiation is being absorbed by my tissue, by the tissue in my mouth. That is of importance from a health perspective. So radiation absorbed is something that we are interested in from a health perspective. We're not interested in how much is being emitted by the X-ray machine and so on. So that's of no consequence for us, right? So it all depends, like I said, on what is the practical outcome that you are interested in. Then we come to RADS. Radiation absorbed dose is how much energy in terms of ergs is being absorbed by per gram of substance. It is applicable to any form of radiation. So 1 rad is approximately equal to 1 Rontgen for water and soft tissue, like human tissue. 100 rads, this is the old unit, is now being replaced by grays. So 1 gray is 1 joule per kilogram. It's a physical quantity. You can see the similarity. And 1 gray is the deposit of 1 joule of radiation energy per kilogram of matter or tissue. Then we come to radiation effects. Now, even absorbed radiation is not sufficient for us to understand the biological effect. I want to know, let's say, a particular person, especially, let's say, occupational exposure for a particular human being. Let's say somebody is working in the radiation lab, and we want to know what is the biological effect of long-term exposure to low levels of radiation. So in that case, we want to look at it in terms of the effect of radiation on the tissue of that person. So then we use a unit called REM. REM is short for Rontgen Equivalent Man. It's based on different biological effects on human beings. A 10 rad dose of beta particles is approximately equal to 1 rad dose of alpha particles, and they would have the same REM because the impact is the same. Okay, so the REM is the same based on impact, even though the radiation is different. So you can compare the impact based, even for different radiation, you can compare the impact. So you have 100 REMs, the old unit, and compare it to the new unit, which is sieverts. So now grays and sieverts are the new international units. And sievert is also similar to gray. It's 1 joule per kilogram, but it's in terms of biological effect. So the sievert represents equivalent biological effect when 1 joule of radiation is deposited on 1 kilogram of human tissue. So if you're wondering how that is done, it's very simple. Let's say you're thinking in terms of occupational exposure to someone who's working in a radiation lab. So you would divide it by the body weight of that person. So if that person weighs, let's say, 70 kilograms, and you know exactly how much energy is there in the radiation that is being absorbed by his or her body, then that is, you convert that to joules divided by the body weight to get joules per kilogram. No, it's not experiments done in the lab. It's just these kinds of measurements. There are several. Okay, then we come to, so that's all about radioactivity. We now move to toxicity. Toxicity is measured in many different ways. There are several standard procedures for measuring toxicity. What is the underlying goal? The goal is to determine the leaching potential, or let me put it another way. The goal is to understand the toxicity of the leachate coming out of liquid or solid mixtures. Okay, there used to be an old procedure called the extraction procedure toxicity test. No one uses it anymore. And now we have the toxicity characteristic leaching procedure. In India, we are following the US in many of these things. And the TCLP is the US EPA's method for determining the toxicity of leachate coming out of landfills. I will be telling you a little bit more about that in the next topic when I talk about solid waste, but landfills are becoming more and more, um, they're going to be reduced enormously all over the world. Most people are now realizing that land is a precious commodity and we don't want landfills. But whatever there is already, that needs to be monitored, and the leachate that is coming out of these landfills needs to be monitored in terms of toxicity. So over time, water and other liquids will percolate through the landfills. This percolating liquid will react with the solid waste that is there in the landfill, and if it goes untreated either into the surface water bodies or into the groundwater, it can pose public or environmental problems. So this is the underlying goal of ensuring whatever is there in the leachate is treated before it is discharged. Let's move on to another thing, and that is labeling. This is something I feel that is important from your perspective, because when you see these symbols, or when you see orange colored containers or red colored containers, the instinctive reaction should be that this is dangerous material. Okay, so biohazard has this symbol. These are three intersecting circles on an orange background. You can see it on containers, you can see it on plastic bags, and all that it means is that people with authorization only should be handling these materials, not anyone and everyone. The kinds of containers we use for hazardous materials, depending on the nature of the containers, will be different. So if you're working in the lab, you might have certain types of containers for dumping broken glass, for needles, for biomedical types of waste. So there are all kinds of things that are shown over here. Radioactive symbol is these three red triangles around a circle. It's always red on a yellow background, and these are some very common symbols, and the whole point is that these symbols should be apparent to anyone without an education too. So anyone who sees these symbols will instinctively know that this material is hazardous. Before we go too far, we need to come to another major point, and that is, if you are handling, let's say you have to, for various reasons, you have to handle hazardous waste. How will you determine whether it's okay to handle them, whether it's okay to mix different types of hazardous waste? So the CPCB report, this is from a CPCB report, and it itself has been borrowed from US EPA methodologies. Anytime you are mixing different waste streams, the first thing you have to take care of is the compatibility of hazardous materials. Are they compatible with each other? Like I said, if you add acid to water, what will happen? If you add water to acid, what will happen? So you know which way it's going to be hazardous. So here we have, so if I add a few drops of acid to water, if I add water to acid, it will cause an explosion. If I add a few drops of acid to water, then it will be, that's okay. Yeah. So that's one example of how you can have hazardous conditions, right? So here we have a whole bunch of different types of chemicals. So we have oxidizing mineral acids. Now, if you're going to mix them with aromatic hydrocarbons, how do you know what will happen? So this kind of chart, and this is just a fraction of the entire chart. Okay, so anytime you're mixing two materials, you should know what is likely to happen. So if I'm going to mix aromatic hydrocarbons with oxidizing mineral acids, HF is the outcome, and that is H stands for heat generation, F stands for fire. So not only will heat be generated, but there is a strong likelihood of a fire. So these are definitely incompatible, right? So consulting a chart like this is absolutely essential to ensure that the outcome of mixing two types of waste is not going to be hazardous to the people who are doing this work or to the people around them. So there are several combinations. You can see all of them. You can have explosions, you can have flammable gases, heat generation, fire, toxic gases, solubilization of toxic materials. All these are hazardous outcomes. And unless you know that two streams should not be mixed together, in otherwise you will have these outcomes. So, and this is not a complete chart. Like I said, over and over again, this is just a fraction of the total chart. You must make sure that you consult someone if you ever think of doing it. Okay, then we come to someone who has expertise in dealing with chemicals and so on. Okay, before okay, we are now going to start with another topic within this, and that is xenobiotics. Now, I've already mentioned that pesticides are a major issue. These are hazardous materials, and I've said a little bit about it in the introductory class when I was talking about bioconcentration and log KOW and so on. Okay, so we'll focus on pesticides in this particular case. These are xenobiotics are defined as synthetic organic compounds that are relatively alien or foreign to the environment. These include herbicides, pesticides, polyaromatic chlorinated biphenyls, ulta kar diya, polychlorinated biphenyls, and polyaromatic polycyclic aromatic hydrocarbons, which can be both natural or synthetic in origin. And then we have chlorinated solvents. All of these can be hazardous or toxic. Now, these synthetic organic chemicals can be toxic to higher and lower organisms. We saw that in the previous topics. They are a source of pollution problems. They can cause short-term as well as long-term health effects depending on concentration and routes of exposure. Now, xenobiotics can be degraded by by all of them, physical, chemical, and biological reactions. We'll take a look at all of them in subsequent slides. I don't know if I mentioned all this. Did I talk about pesticide manufacturing? No one is there, right? Is anyone listening?
Yes.
No, ma'am. No, ma'am.
No,
You haven't discussed.
I have not spoken about it. Is that what you're saying? Yeah.
Yes, ma'am.
Okay. All right. So at the time when Rachel Carson, she published her book in 1962, for about 10 years before that, people were manufacturing pesticides. And like I said, there was rampant use and abuse of pesticides. In those days, these pesticides were manufactured to be persistent. So if you think again from an economic perspective, if you think from the perspective of a farmer, his biggest problem is how to control the pests that are destroying his crops. So if you give him a pesticide that is going to last the entire growing season, he's a very happy person because he thinks, okay, I found the solution to my problem. So in those days, these synthetic organic chemicals were designed to be persistent. And it took about maybe 10 years or even more for people to realize that these pesticides were accumulating in the food crops, they were accumulating in the tissue of human beings, birds, and so many other animals. Again, in the 50s and 60s, the mutagenic and carcinogenic potential of these compounds was also becoming obvious, and that's why she wrote her book. She was a biologist and she was able to put all this information together. Now, once this understanding became public, when it became public knowledge that these pesticides were harmful, yes, they were helping to destroy the pests, but they were also destroying the health of higher organisms, which we, including humans and the organisms that we would like to see around us. So, birds and animals were becoming endangered species and all of that because of rampant use of these synthetic organic chemicals like DDT. And there are so many examples by now, and her book is full of examples. So I have uploaded her book. It's freely available on the internet. You can read it for yourself, and you'll find it interesting, those of you who are interested in this issue. So once this long-term environmental impact of these compounds became known, there has been now a complete change in the philosophy behind the manufacturing of pesticides. So now the pesticide manufacturer has a responsibility, and that is to prove, before they market the pesticide, they have to prove that the pesticide is not persistent, meaning that it will degrade very quickly after it is applied to the environment. So if I am using some chemical in my environment, that smell, that chemical should not be there for more than, let's say, 24 hours or 48 hours or whatever it is. So it should degrade rapidly after it is applied. I have already, so these are the exposure pathways. Now this is another example. This is, one is about pesticides. This is an industrial example. Let's imagine that there is a mine and there is a huge amount of waste ore material that is being thrown into the normally if you go to a mining area, you will find that huge amounts of waste ore is dumped in barren areas around the mining area. Those are called ore tailings. So these ore tailings, they may not have commercially useful amounts of the metal or any other substance that is being extracted, but they do have low levels of the heavy metal that is being extracted. Now, this heavy metal, which is there in the tailings, is in contact with soil, it's in contact with terrestrial vegetation, and when it rains, all that rainwater will carry the soluble material to the surface water body. So when it reaches the surface water body, it will affect the aquatic plants, it will affect the aquatic organisms, and all of this food, whether it's terrestrial flora and fauna or whether it's aquatic flora and fauna, eventually it will come to your table. Okay, so food, air, water, all of it is going to be affected by whatever is contaminated and dumped on the surface of the land. So this is when I was talking about old and defunct industrial sites. These are examples of exactly that. It will contaminate the sediment. It will become a long-term environmental pollution issue. It will contaminate the water, the soil, you name it. Every part of the environment will be contaminated. I've already explained the octanol water partitioning coefficient, right? Everyone remembers that? The bioconcentration factor, the bioaccumulation factor. So this is part of it. I will skip that. Does anyone remember, or does anyone have any issues? Answer, please. Yes or no?
Yes, ma'am, we can skip that part. This part.
Okay, thank you. Please answer. So I've already covered this whole idea of bioaccumulation and bioconcentration, and you can see that it applies not just to synthetic organic chemicals, but it also applies to metals. So here you have aldrin as a pesticide, then you have arsenic. You can see the bioconcentration factors. Then you have benzene. Chloroform is formed when you add chlorine to water, and that is also something that can concentrate in the tissue of organisms. Chlordane is another pesticide. You can see the bioconcentration factor. It's 14,000 in comparison to all the others. Let's take a look at DDT, which has 54,000, and polychlorinated biphenyls and so on. So you can see the bioconcentration factors are enormous. Already explained all of this. Did I talk about DDT? I need some answers. If you guys don't answer my questions, I won't know what to skip and what to say. Okay, I'll just say this. So DDT is what I'm using as an example over here. DDT was invented in 1874. Its insecticidal properties were discovered much later in 1939. It was considered the magic wand in the literally in World War II, because it worked against two major diseases. So soldiers who were out in the jungles and all, they were suffering from malaria and typhus, and DDT was a good mosquito repellent, and this was literally considered a sort of magic bullet in a sense. But when the long-term consequences on birds and so many other organisms became apparent, including human beings, then most countries started banning it. It basically happened after the publication of Silent Spring. Take a look at the half-life of DDT and its intermediate product. So DDT is the parent chemical. It starts degrading. When it degrades, it becomes DD. This is not O, this is DDE. So one of the chlorines is lost. So you have DDE and DDD. Okay, so in different parts of the environment, soil, sediment, water, and the atmosphere. The parent compound in soil has 4 to 30 years, in sediment 1 to 4 years, in water it's 26 to 56 days, and in the atmosphere just a few days, 1.5 to 3 days. These are the intermediates. As it starts degrading, it's not necessarily biodegradation. Biodegradation is one pathway, but there are other pathways as well. So these are the days that it takes for the intermediates to degrade. And these intermediates, some of them, so these can be equally or more toxic than the parent compound. So that is the thing that I wanted to mention about prohibition of DDT. At least in the US, it was in 1972. India followed suit much, much later. But the WHO has allowed or recommended reintroduction of DDT for malaria control, because the sad fact of the matter is that mosquitoes seem to be resistant to every chemical except DDT. So under constrained conditions, use of DDT for malaria control has been reintroduced. I think every one of us who has suffered from malaria, mosquito-related diseases knows how troublesome this issue is. So when we think about bioconcentration, this is the nature of DDT in the environment. So let's say you have 3 PPT. PPT stands for parts per trillion. So in this case, I hope everyone is familiar with parts per million and the conversion to milligrams per liter and milligrams per kilogram. So if you're dealing parts per million, ppm is 1 part per million is equal to 1 milligram per liter for liquids. And assuming that 1 liter is equivalent to 1 kilogram, this is based on that. And then for the tissue of different organisms, so 1 ppm is equal to milligrams per kilogram. So that's 1 in 1 kilogram. So ppt is 1 in 1 trillion. So you can convert it from 3 ppt, you can write it in the form of ppm. From water, it goes to phytoplankton. The phytoplankton are utilized by the zooplankton. Zooplankton I've already shown you in the ecology class. So that's 0.04 ppm. You can see orders of magnitude accumulation of DDT from water to zooplankton. Minnows are small fish. You have 0.5 ppm, and large fish 2 ppm, fish eating birds 25 ppm. So that's how it concentrates through the food chain. What are the factors that affect pesticide persistence? So let's come to environmental factors that lead to the degradation of a pesticide. First is sunlight. You can have photodegradation of a particular compound. So this electromagnetic radiation from the sun will break down the chemical bonds and create breakdown products. And if there is sufficient photodegradation, you can have complete oxidation of the compound. If you have microorganisms in that system, bacteria and fungi are well-known microorganisms that can break down, and that's where we call it biodegradation. When animals and plants take up a particular chemical, not because it's food, but because it's there in the environment, that will change the chemical into forms that may either dissolve better in water or it may lead to certain other toxic intermediates. In either case, they can be removed or they may accumulate. So DDT is a very good story in that sense because the intermediates, as far as I remember, are sometimes more toxic and can accumulate to a higher level. Let me just check that. Yeah. So DDD is just a little bit less than DDT, than the parent compound. So that's the intermediate, yeah. Then water. Water itself is a reactant. It can cause hydrolysis. It can break down the compound. It's a very slow process in general. And you can have dissociation of the compound depending on the nature of the compound. I should also mention at this point that something like DDT, which is heavily halogenated, is very difficult to break down. It's very toxic to bacteria and fungi, so it's very difficult to break it down, but it's not impossible to break down. So that is it's very slow, it's persistent. The biggest problem is it's persistent, and it's persistent because it's so difficult to break down. Then we come to sorption. These chemicals will stick to any surfaces. So any particles that are there in the environment, the best example is soil. So imagine that a farmer is spraying DDT on the fields. That chemical will stick to the particles in the soil as well as the plant surfaces and so on. So that is called sorption. And these chemicals will accumulate to some extent and become inaccessible, or they will move along with the particles. So if these particles are being washed with the irrigation water into the surface water body, then that's how the DDT from the field is being transferred to the water body. And that water in the water body is our drinking water supply. So that's how it enters our drinking water supply. So that's an example of how DDT might travel in the environment. Then we come to bioaccumulation. So there are chemicals that will be absorbed by plants, by animals, from soil, water, food, air. All of this can happen and they will accumulate over a period of time. So as there is continuous exposure to the chemical, you get accumulation over a period of time, and that will lead to toxic effects. Here is a Here's another example, not DDT but permethrin. Now, this is a pyrethroid, and if you look at the kinds of products we are using these days, they are all pyrethroids. So the most common pesticides that are being marketed these days, All Out, Good Night, all of them, they are all pyrethroids, and permethrin is another pyrethroid. So transmethrin, cypermethrin, permethrin, they are all examples of pyrethroids. They degrade more rapidly than the other compounds. So the half-life, when we talk about half-life, we assume that every one of these chemicals is degrading by first order reaction, and you can measure the half-life in terms of the degradation of the parent compound and how long it takes for it to degrade. So every chemical will have a different half-life depending on which part of the environment it is in. So I've already shown you an example of DDT. These are examples. The first one is an example of permethrin, and in this chart below that, you have different insecticides, 2,4-D, capsaicin, dicamba. They're not common in India. The ones that are common in India are pyrethrins. Okay, so taking a look at permethrin, in soil, it has a half-life of 40 days. Let me say one more thing. If I ask you to solve problems, assume when nothing is mentioned, assume it's a first order decay reaction. Okay, so if I say if the half-life of a particular compound is 1 year, what will be the concentration 5 years later? So you should be able to do those kinds of calculations. Okay, so that's the main reason for showing it here. Then in soil, we have 40 days. In water, it's 19 to 27 hours. In sediment, it can be more than 1 year. On plant surfaces, it can be 1 to 3 weeks. It all depends on the specific environmental situation. And indoors versus outdoors, all these are factors that will determine whether the chemical degrades or not. So it's not easy to make any generalization, but knowing the half-life in a particular environment, you should be able to do the remaining calculations. I'm going to skip this one. Then the next one is freight and transport. So I've mentioned all of these things. So you have a landfill, you have leaching from the landfill, it will pollute the groundwater. Any runoff from the landfill will end up in the surface water body. It will affect the plants, it will affect the soil, all of that. And then there are emissions from the landfill. These will enter into the atmosphere. You have wet and dry deposition that will come down either with rainfall or with particulate matter and fugitive dust. So this is one example. And then you have another example where you have the runoff, all the processes that are going to affect the nature of the contaminant when it enters the environment. So it will flow with the runoff, it will get degraded by sunlight. There is some amount of volatilization that can happen. You can have precipitation and solubilization. You can have absorption to the soils and the aquifer materials. That's what is shown over here, adsorption and desorption. And then when you have precipitation, you will get sedimentation as well. So all this can happen. Then you can have biodegradation if there are microbes in the environment. If the material is influenced by pH, then acid-base equilibria will become another factor. Hydrolysis, like I said, is another reaction mechanism for the degradation of any compound, and bioaccumulation and bioconcentration I've already mentioned. And then in the environment, you also have another set of conditions, and that is the presence or absence of oxygen or air. So you will get reducing conditions or oxidizing conditions depending on that, and that will again affect the fate of the compound. What should we do? I think I'm going to cut this down. Yeah. Can I go on for another 10-15 minutes? Is that okay for everyone? It'll take me another 15 minutes to finish it. Yeah. Okay, so what are the treatment methods? The first thing, when you have hazardous waste materials in the environment, you first need to control the source. So source control is the first thing. Treatment, containment, monitoring, and population relocation are subsequent things that need to be done when hazardous waste material or hazardous material is released into the environment. So in situ, you will have stabilization. I can skip all of this, but these are some of the treatment methods that can be used. In situ means that instead of removing the material from its location, you provide treatment where it is in its location. That is in situ. Ex situ means you remove the material from the location in which it is and take it to a treatment plant or facility. Bioremediation is one big one. I'll show you a couple of examples in the next few slides. If the groundwater gets contaminated, there are several options. I'm going to show you pump and treat, and there are several others. Yeah. I did not do this one. Skip that. Okay, let's come to in situ bioremediation. Now, what is in situ bioremediation? Let's say a particular chemical gets into the groundwater. How can we treat it? The first thing we need to do is, there are native organisms, microorganisms, that are likely to be present in the subsurface. It all depends on the depth of the groundwater. So if it is shallow groundwater, it will be high in microorganism concentration. If it is deep groundwater, it may or may not have sufficient microorganisms. Depending on the depth and the presence of microbes, you want to stimulate the growth of these microorganisms. So you can use the natural metabolic activities of these microorganisms to degrade them. You can provide aeration. So one of the things for aerobic microorganisms is they need air and oxygen. So you can do that. And you can add nutrients. So that is how it can be done. So these synthetic organic compounds can be degraded under either aerobic or anaerobic conditions. I'm not going to go too far. I'm just going to end this topic with one example. So I told you in the beginning of this topic that there was an oil spill from the Exxon Valdez in 1989, and huge lengths of beaches were basically destroyed because of this layer of oil that had come on these entire beaches. Okay, now the question was how to treat it, how to bring it back to its original state. This oil is not easy to degrade for the simple reason that even though oil is biodegradable, but you can see it doesn't mix with water. So you have these oil droplets in water and the bacteria are all around it. So these bacteria are capable of degrading oil, but it's going to be a slow process for the simple reason that oil and water don't mix, and the bacteria need water. Their nutrients are in the water and they can swarm literally on the surface of the oil, utilize it as a carbon source, and that's how it can be degraded. So what was missing here in nature is the nutrient supply. So this white patch was sprayed in this particular example with a mixture of inorganic nutrients. Oil is high in carbon. That's sufficient. But the other inorganic nutrients is what was done over here. And you can see over a period of time, this patch has shown better results in the sense that oil on this patch has been degraded and the other patches are dark because of the oil. Okay, so simply stimulating the growth of native microorganisms and allowing them to treat, or rather to utilize the oil as substrate along with the use of inorganic nutrients. Remember the law of the minimum. I've already explained that that as long as all the other inorganic nutrients that are required for growth are in plenty, the bacteria were able to degrade the oil. So that's a very good success story about remediating an oil spill. These are some practice problems, and I will be uploading the slides soon, so you can do them. And don't forget to finish your assignment. So that's the end of our lecture today. That didn't take 15 minutes. I've skipped some things. So if you have any questions, ask. No questions, right?